Okay, so this video is all about masking, why we study masking, and particular details about masking. As a review, the range of human audibility is from 20 to 20,000 hertz. Remember, the ear is most sensitive in that 1 to 3,000 hertz region. So as we went over, 0 dBHL is a calibrated unit that we use in hearing testing, and it varies by frequency. And so in the low frequencies, 125 hertz, 0 dBHL is about 45-ish dB SPL. And so, but that is equally audible as 7 or 8 or 9 or 10 dB SPL in this region. Okay, so that's a calibrated unit we use for hearing testing. We talked about masking being any kind of signal that interferes with the perception of another signal. And it's expressed in the difference in the threshold with and without the masker. So the example I gave is if without any masking, somebody hears a tone at 5 decibels, and then you add masking, and then it takes 15 decibels to hear it, the amount of masking is 10 dB. Okay, so music, conversation, as I mentioned, mechanical noise, anything can act as a masker if it's distracting. So in clinical audiology, these are some of the types of maskers that we use. Pure tones, white noise, narrowband noise. Remember, white noise is characterized by a frequency distribution in energy that's pretty flat across all frequencies, but narrowband noise has a more narrowband frequency representation. So one concept that is a difficult concept to understand is the upward spread of masking. And that's why I want to do a video and get you some of this information before we talk about it in class. So basically, if you remember the cochlea, let me go to the picture. And I had this made for the book because I feel like this is the best visual that I could come up with and I've seen. So if you think about the cochlea, at the base you have a high frequency energy right here, okay? And then mid frequency energies are right there, and then high, mid, and low frequencies. So if you remember, the cochlea, the tonotopic organization, states that high frequencies are represented here, mid, and then low frequencies, okay? So when you think about any low frequency that stimulates the basal membrane, like this here, okay, must travel through the high frequency region, okay? But the same is not true for high frequencies. So if you were to look at this, the high frequency sound here doesn't travel through the low frequency region. It stays pretty tight here within the high frequency region. But low frequencies travel all the way up to the apex. And in doing so, they sometimes, depending on the level, can mask out a high frequency signal. Okay? So again, this is just because of the physiologic function of the basilar membrane that this occurs. So if you have a fairly intense low frequency signal like this, it can mask out a high frequency signal that's a little softer presented at the same time, and that's shown here by this envelope. So this is the signal is here, but the envelope is just like an outline of how that signal stimulates the basilar membrane. And you can see that this lower frequency signal in the lighter blue kind of swamps out and consumes this high frequency signal here. So that way, so in essence, it would not be audible, but the low frequency would still be audible. Now, if this high frequency signal was above this envelope, then both would be audible. But because it's not, it is inaudible. Okay, so the upward spread of masking is essentially when you have a low frequency signal of sufficient intensity that masks out high frequency signals. Okay, It's an upward spread in frequency, but really a downward spread along the basilar membrane. So a low frequency signal will mask a high frequency signal with much more ease than a high frequency signal can mask a low frequency signal. And that's shown in this visual. Because again, all low frequency signals pass through the high frequency region. Okay. Now I know this concept's a little complex, and we'll talk about it again. So that's from a kind of basilar membrane perspective visual of the upward spread of masking. So here we have the same concept shown in a different way. Okay. So here you have a masker, a tone that's at 400 and some hertz, okay, and then there's a masking noise added, okay. So if you add a 20 dB masking noise, that's the amount of masking it provides. If you add a 30, a 40 dB, a 50, a 60 dB, that makes sense. And it masks around that tone. As you go up to 60 and 70 and 80, what you start to see is this additional masking that spreads upward to higher frequencies, okay? Especially at 80 dB, and if you did 90 dB, it would be even greater. Now, there's a visual of this in your book as well. But when you have a kind of lower intensity, low frequency masker, around 400 and some, the masking is pretty localized to that region. But as you go, as you go up in intensity to 70, 80, 90 dB, you start to see this additional high frequency masking that occurs. And that occurs because, if we go back, so as this low frequency masker gets greater in its intensity, so the envelope starts to get very high up here, right? You're increasing the intensity. It starts to mask more or additional higher frequencies. Okay, so it's all physiological, but perceptually it results in this higher intensity, low frequency sounds more easily mask high frequency sounds when presented simultaneously. Okay, let's go to the next slide. And we'll go over this again. So narrowband noise is restricted in its frequency range, and it has a more narrow region of energy. Okay, and these types of noises produce the greatest threshold shifts in frequency regions that are closer within those frequency boundaries. Okay. So whenever the noise is focused and present in a more narrow range, it provides a lot of masking, better than pure tones, better than wideband maskers, and you'll see why. So if you remember, a white noise is characterized by frequencies that are pretty equal in intensity across the frequency region. It has its greatest masking effect between 1 and 4,000 hertz. Okay, and I want you to think about why that is. Okay, why does white noise masking produce the greatest masking effect between, let's say, 1 and 3 to 4,000 hertz? Okay, and then we'll talk about that. I want you to think about that before we answer. And white noise provides a more generalized masking pattern than the narrowband noise. In audiology, we use narrowband noise a lot because we want to focus our masking attempts or efforts, I should say, on a particular frequency region and not just a general masking. Okay, and I have a visual that should help you understand that. And again, for narrowband maskers, the test frequency should be kind of centered on that masking noise. So we talk about 0 dB effective masking level. This is essentially where the masking starts, right? You may present masking and it have no effect on the identification of a sound until a certain point. Once you hit that point, that's 0 dB effective masking, and then it goes up from there. So noise of a 20 dB effective masking level produces a 20 dB threshold shift in the tone being tested. So it's a linear relationship. So here's a visual. So here's the threshold, okay? Threshold. And then when you add the noise, then you start to see the threshold shift. And as you add 10 dB of noise, you get 10 dB increase in threshold, okay? We call this region here the knee point because that's where it goes into this masking, this threshold shift region, okay? So it's a pretty simple concept. The amount of masking is equal to the amount of threshold shift because of the noise presence. Again, there's a one-to-one relationship. Again, we just talked about that. For any test frequency, the narrowband noise reaches 0 dB effective masking level at a lower intensity level than white noise, okay, because the narrowband noise is a more effective masker, okay? All of the energy is concentrated in what we call the critical band, which is the next topic soon here that we're going to talk about. The critical band is the auditory system's way of processing sound information, okay? The threshold shift is the numerical difference between the threshold in quiet versus the threshold when there's a masker present. Now, this is the part that usually takes a little while to grasp. And in chapter, I believe it's chapter 6, there's a discussion of the critical band. If you think back to the to digital filters, right? We talked about low pass filter and high pass filter. We also talked about band pass filter. And band pass filters have... I'm trying to get my pen. Hold on one second. Bandpass filters have a shape something like this, where they pass everything on the inside and then they filter everything on the outside. Okay? So that's a bandpass filter. Oops, I can't get the pen to write. Where it passes only information within the bandwidth of the filter and filters out everything else, okay? So when we talk about, so the auditory system acts as a bunch of bandpass filters. I'm going to show you a visual. So the critical band essentially is the auditory system acts like this. And so anything that's outside of this, okay, any noise that falls outside of this has no effect on the threshold or the ability to hear the sound. Now, stuff that falls within it obviously does, okay? And again, narrowband noise is more effective because it's concentrated in that region. White noise falls outside of it. And again, we talked about this. Narrowband noise are more, yeah, that's the same thing. I feel like I'm clicking on the same slide. Maybe I accidentally hit copy paste a bit. So here's a good visualization of that. So let's take a look. All right, these are the bandpass filters that we talked about. The auditory system acts like this. This is the way it filters sound to help you hear frequencies or sounds of different frequencies, okay? So this is the best visual I could come up with. So if we have a particular tone that's being played, and that tone falls right here within that critical band, okay? If you use a narrowband noise, you know, you have a little bit outside of the band, but most of the noise is concentrated within that band. So this noise, everything in here, let me get a different color here. Everything within this critical band will affect that perception of that tone. Whereas here in the white noise condition, anything within here will affect it, but obviously anything out here has no effect. and doesn't raise the threshold of that signal. And so that's what we mean by it's not an effective masker, because the narrowband noise is concentrated in that band and therefore causes masking to occur.